Join us. I will first go over a few of the logistical matters for today and then introduce our presenter, Rick Haynes. This webinar is scheduled for 1 hour. If we have extra questions, it could go past 1 hour, but we will definitely cover all of the content in 1 hour. We are recording today's session. You will receive an email within 48 hours with a link to our website to view the recording. You will also receive a copy of the slides, which will be sent to you after this webinar. You are all muted, and we will not be able to hear you. However, we do encourage you to ask questions, so please text in your questions using the GoToWebinar interface. Please know that as a participant in today's webinar, someone with Smarter Solutions will be giving you a call. If you do not want us to contact you, please let us know in the feedback survey at the end of the webinar. I will now introduce our speaker and Master Black Belt today is Rick Haynes, who is a 20-year Lean and Six Sigma practitioner and is one of Smarter Solutions' senior instructors. Through his career, he has certified as a Master Black Belt, Champion, and Yellow Belt, along with teaching and certifying professionals in all the Lean Six Sigma areas. His personal Lean Six Sigma work has spanned nearly all business types, manufacturing, transactional, along with research and development business. He is a master's degree statistician and has taught statistics in the Penn State University system. He has worked in all levels of business from the entry level up to site engineering manager. And now we'll turn it over to Rick to get us started. Again, thank you for joining us.
Hello, everybody. Thanks for participating. We're going to be talking about the analysis design of experiments. Now, Mallory introduced me, but I'm going to introduce my guest speaker. I asked Forrest Breifogel, who is the author of the book you see on your screen here, and who really process that we're going to be discussing through here. Forrest is the CEO of the corporation I work for, Smarter Solutions, long-time improvement specialist, and I think if you got to know him, you know he learned this starting with design of experiments way back as I did before I started the Six Sigma world. But I want Forrest just to come in and talk about for a moment where this process that we're going to be talking about came from. Forrest?
Yes, thank you, Rick. Yeah, Rick's talking about a topic that I really have a passion about. I was working at IBM in 1975, a long time ago. Took a design of experiment class that basically changed my life. I said, man, this stuff is neat. I took it from a fellow named Bill Diamond. He was kind of ahead of his time, and he had a program called that was written in ATL. And so I really got tuned into the methodology, and I applied it in development, later into product test group. And during that time frame, I started seeing some things that I thought were real powerful in design of experiments, but I thought there was also some things that could fine-tune it so it would be more powerful. And there's certain things that I don't like Placa-Berman designs, and we're going to be going in, or Rick's going to be covering some of that. And so we can get the most information out we can in the least amount of effort. So we've got some spins on it that we found over the years that are really beneficial, and Rick's going to be sharing with them. So again, I'm glad you're attending, and I'll turn it back over to Rick.
Well, thank you, Forrest. Again, we're talking about, in this thing, Lean using design of experiments just to do an analysis. But as Forrest alluded to, there's lots of other places you can use this. I'll talk about some as we go. So today's seminar, or webinar, I guess, we're going to talk really about design of experiment analysis, both for means and variability. And then we're going to do some of the diagnostics. This is a follow-on from a prior seminar about a month ago about the planning for a design of experiments that I used making cookies. That data set was not good enough for this because it didn't have all the aspects I want to cover, so I'm using a dummy data set for today's analysis. You will, at the end of the webinar, get the slides as a copy of the slides as Mallory discussed in the beginning. But I'm also going to do part of this webinar live. You will be getting, I'll call it a journal of the Minitab commands and the discussion we had during it, along with the data set. So if you wanted to do some of this on your own. Again, as Mallory said, please enter questions typed in as often as you want. I'll try to answer all of them because that's part of the fun. It's not a planned speech if you guys ask enough questions. So we have one question we're going to ask of you. Why'd you sign up for this? I know it wasn't $20 burning a hole in your pocket, but why did you sign up for this? Your screen should be changing. Please select the primary reason you attended the webinar. It looks like we got the first one and the third one are looking good. Interest in personal development. Continuing education's coming up. And thank goodness nobody had nothing better to do. I appreciate it. If you'd post the results, Mallory. You guys should all see them. Advancing skill is the number one. I think that's great. All right. Let's move on. As again, I said this is from a prior webinar where we did all the planning. The planning is not talked about as much in Lean Six Sigma training. The stuff we're talking about now is what's really taught, but we're going to go a little bit deeper. If you want to see the prior webinar, it's available on our Smarter Solutions website in the resource library. You have the title right there. You can search on it. I know if you get on there today, I think it's on the list that pops up when you open the window for the Resource Center. It is free, though. It's free because it didn't really have handouts and material going with it that you can use. It was just a discussion. Now, what we're going to be talking about is really a piece of a whole bigger roadmap that Forrest Breitfogel, who you heard from, wrote to lead people through doing a Lean Six Sigma or a DMAIC improvement plan. We're talking about the one block right here, 8.6 on this for the improved phase, about analyze the design of experiments. Now, what are we going to cover? It'll be a fractional factorial for the mean, and we'll do a fractional factorial for the variance. Same data, same matrix, but I'm covering them both mostly because Minitab is a little different, and most people have not necessarily seen design of experiments to reduce variation. We're going to use a 16 trial design, which means 16 tests were done. In our Lean Six Sigma work, we recommend only 16 or 32. What you see in the right here is a screen from Minitab that talks about how to pick the design you want. And you'll notice the 16 runs, third row, talks about from 4 to 8 factors are fine to run. We're going to run 7 in this one. That's a resolution 4. You can see it's yellow and it's got the 4 in it. Resolution 4 means that the two-factor interactions are confounded with each other, but the main effects are not confounded with anything significant. Now, this does come to one of the pre-questions that one of the participants sent in, is what does a resolution mean? Well, it all goes on to a belief that there's, in design of experiments with fractional factorials, we start with a consideration that three-factor interactions are non-existent. So we consider that they don't count, so you never consider confounded with them. Now, that's a fine consideration in most parts of the world. There are times there are three-factor interactions. I'm a chemist by 1 degree, and there are some in the chemistry world that are three-factor interactions. But in general, they don't exist, so it's safe to assume they don't. I'm going to get back to the resolution when I show the first design because you'll see it when you get the alias table, and we'll talk about why it's there. 2 sets of options I'm going to talk about here that we're going to talk about some of them. Center points. Center points are used when you think you have a curvature of a factor. In other words, it's not a straight line relationship. But they also, as a negative, increase the number of trials required because they keep adding more observations. Then there's blocking, which we're not using today. Blocking is a method to protect your analysis from a fixed change that must occur during the test, such as I got to run it with 2 shifts of people. So I need different people, and by doing a block, it tells you when to switch people so that it doesn't affect the ability to estimate the effects of your key factors. Problem with it, it removes a degree of freedom and may reduce the resolution of the design through the use of a block. 2 other ones we will talk about is replications and repetitions. Replication means taking a second observation on the same trial. So it's repeated measurements. But replication is different. Replication means you set up the whole trial and run it again a second and a third time. What it means is that replication has additional variability in it that you set the process back up again. So generally you get another whole, a replication means running the whole test over again. So if you have 16, you get 32 setups. It's neat. It allows for a lack of fit test to be performed, which we will talk about later. But it really increases the number of trials, and it does not improve the resolution of the test. As in other words, it doesn't reduce the confounding in the design. Repetitions, they're easier. You can use them for variability effects, and that's really what we're talking about. Now, if you can afford extra tests, don't do replications. We recommend repetitions. It gives you an advantage. But if you really can do more, consider increasing the resolution of the design rather than repetitions or replications. Resolution is generally a more important topic. Now, what we're going to do is we're going to walk through a test that has center points, and then we'll cover the diagnostics. We'll do it again for variability. Now, this is what the pre-data sheet I sent you about. It's got this roadmap on it. We're going to follow it right here. We're going to go starting with 8.6.2, a little right of center on the upper row. We're going to follow that through, and if you have this with you, lay it down on the page or on your desk. You can follow along a little bit. These are the words that go with those steps we're going to be running, 2, 3, 4, and 5. And this is a sequence that is different than I was taught, but it may not be perfect if you know more about your system than you would as a general experiment, but in any case, this is one of the most robust sequences for DOE analysis that I've ever seen, and I've adopted it as my own. It's also one we teach in our black belt and our master black belt class. These are the menus and mini-tab that we're going to use. The one in green we'll talk about first. The dashed blue ones will be the second half of the seminar. So I'm going to assume at this point we have a design of experiments created in Minitab or input into Minitab properly so we can analyze it. If you have taken one from outside, from some other software, written it yourself, you use this defined custom factorial design that's highlighted on the screen there to make it acceptable. Here is the matrix. You'll see it's in the standard order. It's not randomized. What we have is 7 factors, A through G. Plus and minus 50 were their levels, and then the last 5 are center points. Center points meaning the middle between the high and the low of a continuous factor. We've taken 6 measurements at each combination, set up the next one to run 6 more. Now this data would have been run in the run order, so it was randomized, but it doesn't need to be there for the analysis. This is when you create the design, this is what Minitab would tell you, and it's similar in other programs. As you can see in the top row, resolution is a 4. Now what's a 4 mean? Well, let's look down to the design generators. These are called the generating relationships that the software uses to create the fraction. Now, if you understand, fractional factorial means each fraction, they take half of the observations in a pattern. So this one has 16, which is a full factorial for 4 factors. That means it's actually taking 3 fractions down from it. All right. So if the design generators are E equals ABC, what that means is in the full factorial of 7 factors, we have only kept the rows where the value in the E column matches the ABC column. So and generally it's plus, by reading this, we took the ones where the plus E equals the plus ABC, or the half we kept. And the other one is F, when it matches the BCD column in the same sign, with the third one being G equals ACD. So that says 3 times we fractionated or took half of the full factorial. Now this would be considered a resolution 4 design, because if I look where it goes E equals ABC, that defining equation has 4 factors in it. All right. You can see in the alias structure where I, meaning the identity matrix, is ABCE. What that means is the A, B, C, E column in this matrix for the 16 trials has exactly the same value. In this case, they're all +1. So that's what resolution 4 means. And we see it in the facts down. A is the same as B, C, E. When you get to the two-factor interactions, AB is the same as CE, which is the same as FG. Again, resolution 4, two-factor interactions are confounded with two-factor interactions. Now, I could analyze this with only one single measurement, but I have 6 repetitions. So which would be better, just one or using the average of all 6? Well, hopefully that is a rhetorical question. The average is, of course, better. From the central limit theorem, the standard deviation of a subgroup, the mean of a subgroup is the standard deviation of the data divided by the square root of n. The act of taking repetitions reduces the variability of your data set, therefore makes it a smaller standard error and easier to see significance. So this is always a good thing, means. So I'm going to walk in to analyze a factorial. Not going to be using Minitab. Depending on your connection, the screens may not update as fast as we would like. If it looks like I'm going fast, please type it in and Mallory will let me know. So I'm going to go to this roadmap. If you get it out, this is where we're going. All right. There, it looks like it popped up on the screen. And I'm looking, it looks like you get the whole thing. This is our data set I showed you. 6 responses. And I have the mean response across the row. See, this is the coded data. It's +1 and -1 in each column with zeros. I'll go back and show it with the 50s. Well, I went too far. Display design. And I can go to the uncoded unit so you can see now there's the real data. All right? Think about Minitab. The 4 columns on the left are required to define the design of experiments. The one that's really different from most of the ones we do is the center point column, 1 meaning a corner point, 0 means a center point. Now let's walk through our analysis. To the chart, we're going to go to Stat, DOE, Factorial, and Analyze. All right? Now, I'm going to analyze the mean. And if you look, it says on the little flow chart, we take with all the terms. So I'm going to go here to Analyze Terms, and I guess they're all in here. Let's change them out and show you how to do it. You use the double caret or double greater than sign. It puts all the factors over there. What we've done is what's called saturating the design. I wanted to make sure that because I have 16 trials, that's 15 degrees of freedom, that I get 15 coefficients in there. Okay. Next, the graphs. You'll see it says a Pareto and a normal plot. You can use the half normal if you want, and I will discuss these when they come up. We don't look at the residuals yet. Hit OK, and OK. I'll start by looking at these 2 plots. Then we'll go look at the session window. If you look at the normal probability plot here, what you see is it looks like a probability plot, but it's a bit different in the fact that it has some red dots and black dots, and it indicates the red ones with coding. What it's doing is it's taking the effect value out of the analysis and plotting it on a normal probability plot. Generally, they're centered more with factors high and low. But if you think about it, what we're testing in this case, if I only put random numbers in to a design of experiments matrix, there should be no significant factors, which means the effects, or how much that factor adjusts the data, should be a random normal variable, and all the dots will fall on the straight line. So anything that's off the line is a good indication of significance. Now, this only works well because I had all the extra factors in there. The other chart we have, which is the Pareto chart, which is my preference on them, what this does is it talks about the effect and plots them as an absolute value on the chart. And you can see, right now, D is our biggest effect, and you can see its magnitude versus B and E. Then comes 2 interactions, then a main effect, then 1 interaction and a main effect. The point of this step is to decide which interactions should I examine further for significance? Now, this is where every practitioner picks the ones they want. Me, I generally pick everything that seems to be captured up with the majority of the main effects. So I would pick AG, AC, and AF. The goal at this point is to drop as many factors as you can, or columns and interactions, so that I get a good standard error or error measurement. Now, because this has center points, it actually can do a significance test. I'm going to scroll up in the session window just to show you. This is the table of fits right here. Notice that none of the observations actually have residuals because I have over-specified the model. I'm fitting 15 parameters or factors with only 16 trials. Therefore, there can be no residual. So that's why we don't look at residuals yet. We have a question? Oh, Mallory said nobody sent a question in yet. I am either doing a very good job teaching or I'm just, I don't know. You can pick. I'd like you to put questions in if you have them. So let's go back now. What I would do is I would write down from my Pareto plot, I'm going to keep AG, AC, and AF. So I go back and we're going to redo the analysis. So I call it back up. Still the mean, but the terms now, if you look at the next block on the chart, you take all your main effects, which is changing this, that's all my main effects, no matter what they showed on the chart, and then the interactions that I want, that I picked from that list. Now what you may note is that Minitab only shows the interactions in the order they show up here. So that's why all these have A in them. AG, next one's AC, and the last one was AF. So now I have the main effects and the 3 interactions that I chose. I'm going to go to graphs, turn off these plots, because without the extra terms, these plots are not as useful. And hit OK. At this point, I only care about significance. If you look at the next operation and scroll up to the coefficient table, here's what it tells me. I think I can make this bigger if I remember how to do this. Nope, I guess Minitab's not doing it for me. Okay. What's significance in this test? Well, if I roll down the list here, if I'm going to use a 5% rule, A is not significant, but B is. C is not significant, but D and E are. F is not significant, G is significant, and all 3 interactions show as significant. And, if you note, there's a center point one. What the center point does, that, remember, if it's got a p-value, it must be a hypothesis test. What it's saying is it uses those middle 5 points to come up with the average in the middle of all the factors. Then it draws the straight line between the corner points and says how far off all of those lines is the center point. If it is not on all the lines or within the confidence interval of the lines, then there must be significant curvature on one or more factors. So this says there is curvature in one or more of the factors. All right, that'll come up later. I didn't talk about that. When do you use center points? The last webinar talked about it. But you should only use center points when you have a belief that there is curvature. I generally avoid using them unless I have knowledge from subject matter experts or other places that say I should be worried about curvature. Most design of experiments don't ever find a region that has curvature, so you can usually ignore it. All right? Notice my R squared is very high. This is a factor of all design of experiments. DOEs, generally I get scared if it doesn't have an 80% or better R squared, whereas if I'm doing regression or ANOVA, I'm happy with 10 or 20% R squared. But it's the nature of the way they're calculated. They always are high. All right? So this tells me all my significant interactions, AC, AF, and AG, but are they the right interactions? This was a resolution 4 design. So I'm going to scroll down to the alias table. The reason at this point on my second analysis, I'm going to go look at the alias table for potential interactions that might be confounded. I didn't look before because they were so big, they had so many things going on, but now I got each of my interactions here. AC, but look at this, is confounded with B and E and confounded with D and G. I'm going to look at them to pick which I think are the biggest effects. I'm going to look at my Pareto chart again to look. Now, do I think AC is significant? Well, it turns out A and C are non-significant. So it's probably not AC. One of the things about interactions, a significant interaction generally will have two significant main effects participating in it. You may see a strong main effect in a non-significant factor in an interaction, but it is almost impossible to have two non-significant main effects create a significant interaction. I know it's mathematically possible. I have not seen it, and I remember asking Forrest a few years ago. He's never seen it either. We know it can. So if I look at AC, it's not that. B and E, though, if you look, are the second and third most significant interactions that I have. So therefore, I'd say that's probably B and E. As I look at the next one, D and G, if you look, G is way down the list, but D is the most significant. Well, it could be that one too, but I like B and E. In this case, this is all simulated data. If I was in real life doing a design of experiments, I would ask my subject matter expert which interactions could exist. Could these interact? So I'd use them to help pick it. I would also build a factor plots, which I'll do that here in a sec, and look at them to go see if not only do I know could they interact, but do they interact this way. So to do that, that's stat DOE factorial, and you'll see down here factorial plots. An interaction plot. I'll put all my main effects in there, and I'm going to look at mean. When I hit OK, oh, I didn't actually get them all over there. There we go. You get a plot. It's a little funny with center points, but I can now see the interaction area. My first was A and C. That interaction right here, you can see it's a perfectly flat line. All right. Remember, I'm looking for non-parallel lines or things that slope. I don't see a lot of interactions in here, but that's how you go look at it. If in the absence of a subject matter expert. Now, since we really have no knowledge of these factors, I'm just going to pick the ones that make sense. So I picked B and E for the first one. Now, what's A and F? If I know A is non-significant and F was, but it was a small significance. So I don't know if I like that one. So I'll go to the next one. We got B and G. Let's see, I'm taking my notes here to make sure that I always get the right answer that I want. B and G. B is significant. G is close. So I like that one. All right. And D and E was the next one. Wow, D and E are two real significant ones. So I'm going to pick the DE interaction right here as the significant one for my selection of the interaction. And the last one, AG. If I look at A and G, A is non-significant, G is a small one. B and F, well, that's significant, but F is on the edge. And the last one is C and D. Well, D is most significant. I'll just pick that one. Now, in reality, you could go any way you choose on these. But in the absence of having subject matter experts, I'm going to pick them based on the most significant pair. So going with that, I do my third analysis now. So I go back, stat, DOE factorial, analyze factorial design. I'll go to my terms. This time, I want to have my main effects that were significant. Move them all over here. I had, if I look back to this, a second, easier if you move this. I'm going to get cancel. I want to get to the point I can see them. There we go. Let's call it back up again. Terms, take them all over. What's significant? A is not, but B is. C is not, but D is. E. F is non-significant, but G is significant. Then I have my interactions that I wanted, which were BE. The next one was DE. And then the last one was CD. All right? It's going to give me an error, though, because I have C in an interaction, and I don't have C in my main effects. I guess I'll show you. You should get it. It says you can't have something in an interaction that is not also listed as a main effect. So I put C in now. Got that? Last one says graphs. We're going to go look at our 4-in-1 residual plot. I'm going to add something new that a lot of people may not have seen. One thing you can tell a lot about residual plots when you look at your main effects. So I'm going to put my main effects down below as an extra set of residual plots, A through G. All right? And I hit my OK button. Look at the overall residuals first. Probability plot, this is testing the belief that the errors are normally distributed. They look good. The upper right is the fitted value versus the residual. So you want this pattern to show no significant pattern variability, and it looks like the variance is equal across the whole range. This versus order one is interested if you think the process may be changing during the running of the test, but since these were in standard order and sorted, I don't use it. Let's go, I'm going to come back to the other analysis, but let's look at the session window now. So I scroll up, I get my coefficient table, and I have B is significant, C still is not, but everything else in the test is significant, but it looked like, in this case, DE became non-significant. Interesting. The significance may change as you add and subtract factors. I'm going to leave it in there for now because it's pretty close to 5%. All right. My R-squared is still relatively 100%, but so I'm in really good shape. I would consider this to be an acceptable regression at this point. So one of the analysis we do in diagnostics is to look at the residuals. All right. The second one we're going to talk about is looking at the residuals of the other factors. Now, what I'm doing is this is A. I'm looking at the 3 levels of A, minus 50, 0, and plus 50, and looking at the residuals. They should have about the same amount of variability at each location. All right. This one looks like it may have a tiny bit of curvature. That could be part of it. Let's look at the next one. That one looks pretty random. Notice about the same width across all of them. Now I hear one that starts, C looks a little odd here. If you look, C doesn't have seemingly as much variability at the low end as it does at the high end. Maybe we have an interesting factor there. Go to D. I admit I've done this before. I'm looking to get to one of these to show you in a minute. That's okay, sort of. Now this one's pretty clear. Look at this. E, it's got a lot more variability at the negative than it does at the positive 50. It almost looks like you could draw a bit of a taper down to a point if you wanted. What you're seeing here is an indication of a factor that may also have a variability effect since we know it has a mean effect. That's why we're looking at these. F, and here's one that looks like it may have the curvature issue. If you look, the residuals at the high end are all high, indicating there might be some effect in there. Now, I'm looking these as the variation eye, but another reason you look at these in your diagnostics is if you have a bad data point or a misentered data point or a real outlier, they show up sometimes clearer in these plots than they do in the other ones. That's why we like them. All right? So we have our answer now. I'm going to go back to the session window. I have a potential variability effect in E, and this would be my equation. If I was to solve it, I could write B. There's my coefficient times the value of B. Then the value of C times this, D times that. I would get my predictive equation. Now, one thing you can look at this, which is the most significant factor for the mean? Well, it would be D, because if you look in the T column, it's the largest magnitude number. The bigger this number is, the more influence that factor has on the target value or the response, in this case, means. Okay. So that was our mean plots. We've done an analysis. Next one is, how about variability? Now, I'm going to go back to my slides now. There we go. This is the output I got. You can see they're significant. I'm keeping DE in there. And the residual plot looks okay, so therefore I'm done. This leads us to our next question. This is as much just to find out what you guys know when you came to this. Which of the topics that we covered there, I give you 5 choices, were new learning points? Ooh. I didn't even cover lack of fit and pure error yet. So if you don't know what they are, I must have skipped right over it. So I'll go back and cover it. If you know what it is. If you don't know what it is, that's a good choice, and I'll show you in a minute. So please answer. It looks to be, you can pick more than one in this, so you can put all that are new. The residuals of the main effects and using the mean for DOE analysis. That's excellent. You post them, Mallory. So it looks like the Pareto analysis was known by many, but some of the other stuff was new. And the lack of fit and pure error. Let me go back to that. Mallory will give me back the computer. I'm going to go backwards a slide. Oh, no, it's a mini-tab I have to go to. That's why I didn't cover it. If you look at mini-tab, right here, this is the ANOVA table. Now, this is version 16 I'm using. If we're using version 15 or earlier, you wouldn't also have the main effect p-values in here. You just would see main effect interactions and residual error. What you notice is residual error is broken into 2 pieces. Whenever you're running a design of experiments, that you end up reducing the number of factors to the point that you have replicates built in. Now think about it. We started with 7. Now we're down to 4 factors. We have almost, with the center points out, we have an idea of what pure error was. And this level, it's really the standard deviation or the variance around the center points. I can compare that to the residual error, the standard error of the analysis, and subtract the 2. Because there's 2 things that create variation around the predicted point. One is the standard deviation of the whole analysis. The other is what's called lack of fit. So you got the variability of all the points at that corner, and does the average of the points in that corner match the average of the prediction? The lack of fit, if that becomes significant right here, in this case it isn't, what it means is you should not be using a straight line model for DOE. You need to go to what's called a quadratic model or something else. It can mean at times you can have an interaction included. It could mean you have to put a quadratic term such as a squared or b squared in there. We generally decide that by looking closely at the residual plot. But that's what lack of fit means. And you will see it mini-tab pop up whenever you use in design of experiments, you start dropping factors. If you ever get a replication built in or use center points, you will get this analysis. Back to mini-tab, or back to our slides. Now, I hope you followed the flow chart. We're going to go back through it again here, but we're going to do a variation analysis. Now, this has always been possible in mini-tab, but they've given us special menus to do it, I think starting with version 15. But they have what's called the pre-process for variability and then analyzing variability. You'll see the real benefit at the end when I run the response optimizer. I'm going to go through this a little bit faster. Hopefully you've seen it once. That's why I gave you that flow chart to follow. Ooh, I wasn't supposed to give you the answer yet. We're going to go do it in mini-tab. All right. Now in mini-tab, I've got my data. I've got 6 responses, and I've calculated the mean already. So let's go through the menu. Stat, DOE, factorial, pre-process for variability. Now what this does is we're going to tell mini-tab the way the design is set up and where the variability columns are. And there's 3 choices. I'm using compute for repeats. So this first section is where are my repeated values? Note it's response 1 through 6. So I highlight those and select it. I have to tell it where to put my standard deviation. So I'll tell it STDEV. And I need to tell it the number of, I'll give it an N. It needs to know how many values in each standard deviation so that it can make proper estimates. Now, if I would have done this otherwise, I can actually have it calculate the mean for me and have created that column. So if this was in real practice, I would have done this first before the means analysis. So I hit OK, and it should give me 2 more columns. It moved them out here because I had done this test before and had something in these two columns before. But there's my standard deviation of each observation. Each has 6 values. Now let's run our analysis. That, DOE factorial. But we're going to model because analyze variability. I'll show you why. Menu's a little bit different. Notice it knows what the standard deviation is in because I told it in the prior analysis. It says here I get 2 estimation methods. I'm going to use least squares. But when I get to, everything else really runs the same. I think when you look, that isn't the one I'm looking for. There we go, graphs. We're going to put the normal in the probability or the Pareto plot again. But notice I've got an extra thing here. Do I want to use residuals for a ratio? A natural log of the variance. Ratio is the ratio of variances, or a standardized natural log. What we're doing is we're going to use the natural log, as it turns out if you've taken our courses. The standard deviation, when you take the natural log of it, is the transformation to get it close to normally distributed data. And you need normally distributed data to use a design of experiments. Now that's not fair. You need a normally distributed error term to run a design of experiments. So by taking the natural log in the background of this standard deviation column, I will get good answers. I don't want my residuals yet. My terms, again, like we had before, you run all of them. All right. I'll include my center points, hit OK, and OK. Again, I get my standard deviation plot, my Pareto plot. This was what they typically look like a little bit more. This indicates B and F, an AC interaction, and an E. Now, we have not changed the matrix at all, have we? We've just analyzed in a different column. That prior alias table still applies. So AC really could be something else. All right. Now, when I look at this Pareto chart, it's not as Pareto-ish as many. Notice they've got B and E and then an AC interaction. So it looks, it's its biggest of other factors, an F, an AE, and then some main effects. So what would I want to analyze in this? Well, I'd probably do the main effects and then only AC and AE. To me, that one's just too far down there. All right? So let's go run it. Again, we're going to have questions at the end. If you have questions now, please type them in. Let's see. Call the menu again. My terms now are, and move this over here so I can see it. I'll go to only my main effects. So I run all those plus which interactions, AC and AE. That's all I have. I go to my graphs and turn off my normal and Pareto plot, and I will look only at the session window. Scroll up to the top. My coefficients. Now what's significant? A, B, C, no D, I get E, F, and G. And both interactions are significant. Huh? Looking good. Now my center point this time is non-significant. It says that there's no curvature in the variance effects. Now, again, here's where I should have done lack of fit before. If you look at the lack of fit term, its p-value is nearly 1, which means this actually predicts extremely well. So the average at each corner is very close to the predicted point. Right. Looking good. So if I scroll up, my next third iteration of this analysis is the significant main effects and significant interactions. I'm going to move this chart over, and the next thing is, are those two interactions the right thing? So I look back at my alias table. Could AC, notice C is down at the bottom, and A is really close, but I could be AC or BE. Well, B and E are my two most significant effects. So I'm going to choose that it's really not AC, it's B and E are the interaction. And this is a very common pattern, by the way. Two significant main effects with its interaction right afterwards. Then I go look at, is AE, A being here and E being the second most significant one. That looks pretty good. We should check them all. B versus C. Now, B is significant, but C is way down here. And D and F. Well, D is here, F's up here, so which one should I choose? Well, I'm going to choose A and E because E is so significant. And A is up here too. All right, my next analysis. Go back to my terms. I'll move them all over, take my significant main effects, which are A. Oh, I'm going to cancel this. Let's go back. So I can put this up here. There you go. My terms. I have A is significant, B is significant, C is not, D is, E is, F is, and my two interactions. So is G. A, B, E, F, and G. Oh, is D significant? A, B, C. No, D is not significant. All right. And which interactions? Well, I chose, I should have written them down, but I chose AC, excuse me, BE and AE. Here's BE and AE. Those are my two interactions. Now I go to my graphs. We'll see on that the 3-in-1 plot. Now, why is it not a 4-in-1 plot? Good question, Rick. The reason, since I've calculated standard deviations, the idea of time dependence doesn't exist. So I've processed the data, so it changes the output because of it. All right. Hit OK. Here's my residual plot. Notice the probability plot's the one that's missing. Why? Because we're really doing the natural log of the standard deviation. Now, we could have, but what's funny about this residual plot is you notice there's one point way, way up higher for predicted variability than anything else. All right? Also note, it's doing the plot in the natural log of the standard deviation. So it's actually behind the scene doing a transformation and running the data. Now, I would look at this. That's an odd point. I'm going to go to brush and highlight it. You'll see it's row number 2. Go back and look at our data. What's row number 2? You notice since I brushed it, it's got the little icon by it here. I think this one. If I look at this numbers. The standard deviation is 231, so it really is almost, it is twice as big as the next largest ones. But if I look at it, it's got a -900 up to a -291. It's got a huge range in values. If you look at the other ones, they're not necessarily as much variability. Here's, if I take row 10, it's got a 650 up to it's got an 800 and a 400. Only a 400 spread. This has got a lot bigger spread in the data. So what we find is that one is high variance. Now I can go back and say, is that a good data point or not? Maybe the 291 is a bad data point right here, but we don't know, being that this is actually random data. This is data that was built from a simulator, so you do get odd points sometimes. So by looking at this, I wouldn't throw out the data point. I must keep it because I know how this data was collected. So we keep going. This looks okay. This looks sort of okay. The only odd point in this, my diagnostics, is this point. So again, you investigate it. If all the points look valid, you use it. Go look at the session window. If you note, everything is significant. I'll also show you here, it says regression coefficients for the natural log of the standard deviation. So the predictive equation for this is for the natural log of the standard deviation, not for the standard deviation itself. But we're doing that so that you have good estimators and good p-values. Lack of fit is also non-significant, so is center point, so we're all set. I'm finished with this analysis. So what's significant for variability? I have A, B, E, F, G, B, E, and A, E. So what? Doesn't help me a lot just with that. Now this is what the last thing I'm going to cover on here is the response optimizer. hopefully you've seen this before. What it really does is it takes the regression answer, or the answers from the DOEs, as if they're regression equations, and solves for them. I'm going to go, I have the mean that I use in this analysis plus C21, which was my standard deviation. I've analyzed both of those with separate tools. I go to my setup. Now, you see I did this one last night to practice. Let me go back, hit F3, so I can do it from scratch. There we go. Okay. When I set it up, I want to target the mean. I'm just going to pick a target of 0 since we didn't really have one. And I want to minimize the standard deviation. We'll start with my target. I want to be at 0. If you notice, the numbers went from minus 900 up to plus 800. So I'll say from 100, I'm giving it a range to try to find an answer in, to 100. Now when I go over to the standard deviation, I have to give it a target. Well, what's the minimum? Well, it's always 0. You need to set an upper limit. Generally, you pick a number that's in the data set somewhere. I'll just pick 50. There was numbers in there. Hit OK, and OK. Now, I'll make this bigger. This top line is one that's called the desirability function. I'm just going to remove it because I don't want to talk to it. Now, what we have here is Minitab selected the best set of combinations to get me a 0 for the target and a minimum standard deviation. Now I can see here that it predicted this combination, by the way, it just happens to be all the center points, as a mean of 6.5 and a standard deviation of 3.5. Now, if you've used this before, and I guess this is one of my learning points from writing this, is those are dots, which means it won't let me interpolate between them. Like I can't drag this line down to halfway. It only allows it to be at dots. Now, I found out on the Minitab website because of this that if you ever fail a curvature test, as in center points, that's significant, it assumes you can never interpolate between your data points, so it will not let you. It will only allow you to select the actual data points itself. So that's what's happening. I've struggled with that one in class teaching, sometimes not knowing why. But note a couple things. See, this is curved. There's a little curvature in that one. Right? It's not a straight line. This one looks straight. Most of them look relatively straight. A little bit of curve here. But what we're seeing, now the standard deviation curves are not as important in the fact that we analyze the natural log of it, which would straighten a lot of these curves out. But that would be my solution then, is it 0 at all of them, and this would predict my answer. Well, that's really where I was going. So it really recommends, the best I can get of this is at 35 for standard deviation with a mean of 6.5. Go back to my slides now. This shows you the last analysis we got. All right, the residuals, again, we investigated the 1 point. There's my response optimizer numbers. Again, it did not allow a solution because I had a significant curvature or center point test.
Question, Rick.
Mallory.
Are the center points the optimum?
They are in this test, but that's not very typical. The center points are just chosen as equidistant between the continuous factors. This data set that I pulled out just happened to have that as a solution. Let me go try something else. I'll go back to Minitab to show you that it can get different answers sometimes. I'll rerun this analysis, but let's pick a different target. Let's take a minus, how about a 500 for a target? We'll make 0 a minimum and 1,000 for the maximum. So instead, let's say my target was to get to 500 instead of 0. Now when I run it, you will note that it actually solved for a different set of conditions. In this case, it's minus 50, or excuse me, 50 for A, 50 for B, 50 for C, 50 here for D, E minus 50, F 50, and G minus 50. But notice it's no longer center point. But in this case, I wanted to target a 500. It said, given the corner points, the best I can get is 656. Right? But my standard deviation in this case is quite small, 3.9. So I get a lot smaller standard deviation up there, but when I get a higher mean. So no, the 0 center points weren't the optimum. It was just because of where I chose to target the mean is where it came out. I hope that answers the question. Just about out of time here. I'm getting a signal. Let's walk through this. Last question. Did you learn anything new here? Did I cover a topic you hadn't seen before? So please pick all that apply. Ooh, the natural log. Coming up to be a big one. Now, being that everybody's picking it, I wonder if that meant this was set up as a only pick one? No? All right. What I didn't tell you is before, other than using the Minitab function for preparing for variance, you could have taken the standard deviation, made a new column with a natural log, and just used the standard analysis package to go get it. You didn't need to analyze for variability. All right. You put it up there, Mallory? Oh, there we go. Most people are analyzing for the natural log. All right. And repetitions instead of a noise matrix. That's a noise matrix being a Taguchi term. Instead of a Taguchi matrix, you can actually use repetitions to solve for the variability, which is what this data set had. All right? So what did we cover? We covered the analysis method for DOEs, and it was really 3 unique sets of analysis on each response. The first one being all factors and all interactions, in other words, saturated, used the Pareto to find potentially significant interactions. Notice potential, because you don't always know how significant they are, because they use so many factors in there, you don't have a good error term yet. So I picked the ones I think that are included up high enough in my Pareto chart, like my main effects, then I run a second analysis. Now it uses all main effects no matter what, and the selected interactions. 2 reasons. One is main effects are always more important than interactions, or more have to be significant, but the act of keeping them all in there makes sure that all the interactions will still exist in the data in case I choose to change them from the alias table. Now I look at p-values to see which main effects are significant, and I check the alias table to see which of the potential alias 2-factor interactions I want to keep. The third analysis is all the significant main effects and the significant interactions as chosen from the alias table. At that point, I verify the residual analysis for acceptability. That's the process. So I've really finished up. I hope you have a few questions. We're going to stay on to answer a few of them if you have any. But I tried to cover DOE for an average, DOE for a minimum to minimize variance, and then the pure error, lack of fit, residual analysis, diagnostics. Any questions?
Can you provide an example of a block in a transactional DOE?
Ooh, that's an interesting one. First of all, can you run transactional design of experiments? And the answer is yes. In this case, what I talked about today was for continuous data. So if you can measure time or some other continuous variable, you can run a design of experiments. Now, what would be a block? It could be 2 different sites that are doing the same process. You can actually block it 4 if you wanted. So different locations, different shifts, different, generally by the people that are executing the process. That's the most common block in transactional design of experiments. You could also do customer-based ones or product line-based. In other words, a block is any factor that is not in your test, but it has discrete levels in it. All right?
Which of your classes do you cover the DOE in?
We cover it thoroughly in the black belt class, our Lean Six Sigma black belt class. We talk about some of the exceptional parts in the master black belt class. We don't spend as much time on the straight up stuff. We talk more about some advanced diagnostics, unique uses of the design of experiments in the master black belt class. In our green belt class, we introduce it. We have a short discussion. We run 1 full factorial DOE to show the potential of it. And if you're using Minitab, just enough of an exposure, we have found that our master black belts can coach anybody through one that's a green belt just over the phone.
Okay. Can you explain interpreting the normal probability plot?
All right. I talked about it earlier, but again, when we're using the normal probability plot, let me go to Minitab for a minute. Go to my session window. I want to go up to one of our early analysis. This should be the first one for variability. It's up here. If you notice, you have an effect for every factor. This was my saturated design. And again, if something is non-significant, the amount of change in the data based on that factor would be a random variable. If it's a random effect, then it would plot on a probability plot as a normally distributed data. Now, because the errors are required to be normally distributed, so should the effects if everything is non-significant. So any one of the effects, this column called effect, that is off the normal probability plot line has a good indication of being significant. But I will tell you that there are some factors that are still triggered as black on that chart that are still significant as we start dropping terms, because the more terms we drop, the better residual error we get and the better we can calculate p-values. So that's the interpretation of it in this case.
Okay.
Any more?
That's all the questions we have so far, but if anyone has a question that they didn't get submitted just yet, please feel free to submit them offline in an email or give us a call, and we'd be happy to discuss them.
All right. Oh, I got to go back to my slides. I have one wrap-up thing to say. You'll get a survey at the end to take. But that roadmap that we showed you, the one you have in your hand, you'll get another copy of it with a journal of all the steps I did with Minitab, so you could duplicate them. We'll also get the data set in a Minitab 14 project. I may send an Excel copy over too, just so you can, in case you don't use Minitab. But that roadmap you have, that's a piece of a huge roadmap that Forrest Brightfogle created for doing a DMAIC project. If you plotted it on the wall, it's 96 inches long and 3 feet wide. It includes every drill down. You can also find it in the book we referenced for this is Volume 3, Integrated Enterprise Excellence book. But it's just one piece of the detail that you can have if you like processes and solving projects. Thank you very much for your time. Anything else, Mallory?
That's it. Thanks again for joining.